Instead, I wish freshmen would, you know?
So you want them to go to another school before they go here?
They should, freshmen, there should be a separate schools for freshmen.
Because, okay, so basically what I said.
My dad went to high school, it was 7, 8, 9, one school, and then 10, 11, 12, high school.
That's how I was.
People that specialize in this field.
Theory that could happen is they extend the school to half such or no?
The electron with the larger
You
weight
have to
because
it
has smaller mass.
support for such.
Oh, yeah, you have.
Yeah, but it also makes sense. You just
That's what I said, that's what I
use
said.
the wavelength equals the H over MV.
That's what.
Yes.
Yes. Shouldn't it just
Okay,
be?
that makes sense. Why is this so confusing?
Should it just be? Because wait, oh, because you have to make that a degree in AI. That's AMU. Smokey the Bear. Oh, wait, yeah.
How? I don't understand how you don't know this stuff there.
Yeah, I know. I try to read it. Yeah. That's what I'm doing. Yeah. I'm reading.
Yeah, but the velocity
I'm not good at it.
Right, that's,
But it doesn't because the energy of
Hey, just because I was born in America does not mean I'm still good with English.
What were you talking about? We're asking about the
well,
both the mass and velocity of the play
never do.
and how big the momentum is.
I swear I did this one, exact one, earlier.
Yeah, neither am I.
What do you mean what am I talking about? P equals MV. P equals NV.
Except that, never mind, I'm gonna say this.
No. P equals NV. You just.
Okay, are we going?
Yep.
Okay. So let's start with this first question on scanning electron microscopes. So one of the cool things, and this is just some of the images, is that you can get an extremely high resolution mainly because of the fact that you can alter the wavelength. So this first question, if you look at whether you want fast electrons or you want slow electrons. So here's the idea of when you're looking at an image. If you want to look at something extremely small, to really get any resolution at all, you need a very, very short wavelength, okay? So this is, again, the fundamental problem with trying to go, oh, hey, I want to see an electron. Great. To see an electron requires, because it's so small, if you want to see it with light, you have to shrink the wavelength. Well, when you shrink the wavelength, what happens to the energy? It goes up. So then you're running into a situation that's like, yeah, I can see it, but I don't know what happened to it afterwards. It was just like you're driving down the road and you hit a mosquito. Okay, great. You found the mosquito, there's not much left of it because of the process of finding it. You destroyed the mosquito. So the same thing is true of an electron. So electrons travel in what they call a wave function, which is this realm of possibilities. And when you, quote, see it, then it's what's known as collapsing the wave function. So, and because now you're making it make a choice. So there's a famous thing that comes out of this. It's called Schrodinger's cat, okay? So if you've never heard of Schrodinger's cat, here's the short version of this. There are literally entire books written on Schrodinger's cat because it's very philosophical. So the short version of Schrodinger's cat is that they had, and this is a thought experiment. To my knowledge, it was never actually performed. Okay, I'm just saying. So if you're a cat lover, don't I can kill the Fluffy. it was a thought experiment, okay, chill out. So inside the box, there is, oddly enough, a cat, okay? Right? Named Whiskers. So there's Whiskers the cat. Also inside the cat, or inside the box, there's a radioactive source that can spontaneously go through radioactive decay and kick out some particle, maybe an alpha particle. And if that happens, it breaks a vial of poison and the cat dies. Look, this is in the 20s, okay? Animal rights people weren't around at this point, so this is the hand that we were dealt. That's why you did the monkey hunter demo where you shot the monkey, okay? So here's, you can't see inside the box. So the cat has two possible states that can exist. It can exist as a live cat, it can exist as a not so live cat. Unalive, if you want to put it that way, okay? So you can't see inside the box, so you don't know which wave superposition the cat is in, alive or unalive. So the only way you can figure this out is to open up the box. So open up the box is like collapsing the wave function. So one of two things is going to happen. Either the cat is unalive, or the cat runs out and goes, I'm never participating in science experiments again, okay? But you don't know until you open the box and you collapse the wave function. So this is what's happening with electrons, okay? Electrons are moving around, and by, quote, seeing them, you then are forcing the electron to make a choice, and you collapse the wave function. So instead of having all these multiple possibilities of existence, you're saying you have to pick one, okay? So there's this realm of possibilities. It's somewhat similar to all of you trying to decide, hey, which college do I go to? So there's a wave function of potential colleges. You collapse the wave function when you pick a college, okay? Otherwise, you've got this realm of possibilities. Hey, we're going to pick one. Same thing happens when you collapse the wave function. So, in terms of the deBroglie wavelength, where you have lambda equals h over p, which is h over mass times your velocity, okay? So if you want a high resolution, you want a short wavelength. Well, you're not going to change the mass of the electron. That's kind of the fixed value. So the only thing you can alter is the velocity of the electron. So if you want a shorter wavelength, you want a faster electron. Okay? Does that make sense? So there's that question. When you get to question number 18, so on that one, this is basically just pretty simple. The math isn't too hard. But the second part is, just conceptually, can an electron, nope, wrong. So, Firefly, okay, what is the minimum chemical energy in electron volts required to generate each photon? So this is for you biology people, okay? Kind of pick that one because of the fact that you've got ATP and all this good stuff. And don't get me wrong, fireflies are cool. So, at the end of the day, you want the firefly to emit light. So, if you're going to emit light, what has to happen? Inside the firefly, what do the electrons have to do?
Hit an object.
No!
They have to change
They have to move out of their ground state into a excited state. They don't like it, they come back in. Okay? So, on this one, you have a wavelength of 550 nanometers, which is in the visible light spectrum. Well, the visible light is roughly 500 to 700 nanometers. Okay? it's okay that we can only see a small spectrum of the entire thing, that we can only see a small portion of it. We don't want to be able to see the whole thing, or otherwise, like, we would be inundated with information. Like, you would see the microwave oven work, okay? If you could see radio waves, instead of like listening to radio waves, you would see radio waves. Like, oh, hey, there's a big radio antenna. You would, just like if it was emitting light, and you would see light in the darkness being emitted from it, you would see radio waves being emitted from it, okay? Which would get really, really weird. So it's okay that we operate in a very small portion of the whole spectrum. The good thing is that we can feel things outside of that spectrum. What's a good example of electromagnetic spectrum that we can feel but yet not see?
Infrared.
Infrared. We can feel heat, okay? It's like, oh, put your hand over the top of the oven. You can feel, you can't see it. It's not emitting light anymore, but you put your hand on it, it's like, oh, right, that's hot, okay? That's a good evolutionary trick to have, okay? That was probably selected pretty early on, okay? Because if you've got Thor and Ugg goes, oh, I can't feel anything, I'll grab hot stick. He's probably not going to make it. Thor goes, wow, I can feel the hot stick, I don't have to grab it. He's probably going to be more likely to survive in the gene pool, okay? So evolution meets physics. So anyway, so you're going to get that so that in electron volts gap, Sean, not joules, your answer to 18A is going to make a not so good GPA. And then it says 1 molecule of ADP provides 0.3 volts. How many is that going to take? That's just a simple division problem. And so you should get like 8 molecules from that. Okay? Now, 23 is an interesting question. Speaking of radio towers. So you got station KIM in Hawaii broadcast AM dial at 870 kilohertz with maximum power 50,000 watts. Maximum power, how many photons does transmitting antenna emit each second? Okay? It's a really, 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 really big number, like 10 to the 31st photons per second, okay? So this is like emitting steroids, or emitting photons on steroids. So here's, and this oddly enough turns into, are we alone in the universe? So ever since we've started broadcasting radio waves, and that was the first form of like mass transmission of information was radio waves. That used to be how everybody got the news, was just they sit around and listen to the radio. So when this radio station transmits that information, it literally goes out into the universe. So for about the past 120 years, Earth has been this beacon of radio waves in the universe. Cool thing about radio waves in terms of traveling through the universe is that radio waves have really, really long wavelengths, so they're not scattered by dust and particulate. So they stay true, okay, as they go through the light. And so the thought being is that if there is intelligent life, however you want to define that, somewhere else in the universe, they would have built the capacity to listen for radio waves because of the fact that, oh, that's the most reasonable way to transmit information. So there's a whole organization called SETI, which stands for Search for Extraterrestrial Intelligence. And they've got these big, massive radio antennas because they figured, hey, somebody's going to respond back to us in radio waves. And they search the skies because they figure, and if you think about it, every year that goes by, the circumference of planets or solar systems, whatever, that are capable of listening to us or hearing us increases by a light year because that's how fast that thing travels. So every year, there's a light year increase in distance of planet solar systems that can hear us. And so the thought being is that they're going to hear our pick up that transmission, maybe they don't know what it is, God forbid, they get like TikTok videos or something. But they're gonna look at that and go, we're not responding, these people are stupid. They have technology and this is what they make. So, but if they just wanna respond back and go, you people are idiots, that you would think we would have heard something by now, okay, since this has been going on for like 120 years. We're over, okay, like nothing. We have not heard anything. And so either they just don't care, or, which I think is a very low possibility, or we're just alone in the universe, which is a whole other daunting question. It's like, cool, we're here. This is it. Entire universe, we're it. We're in G20. Here we go. That's kind of cool. Okay. Anyways, that's a really big number. On 30, that velocity on A should be something times 10 to the 6th. The answer to 30B should be around 2,000 meters per second, give or take. 38, this is, on 38, this is where it's handy to use those kinetic energy equations. Excuse me, on 33, not 30, on 33, my bad. I misread it. I saw the 8. On 33, this is where it's handy to use those kinetic energy equations. Now, when you get to 34, okay, so let's talk about 34. So rubidium atoms are cooled to 0.1 microkelvin. That's really cold. You have 0.10 microkelvin. So if you're going to cool atoms down, the only way you can really get them to this level
It's with lasers.
it's a laser trap. So basically, and again, Kelvin is what atoms feel. So if you think about how you cool things down, so let's say that I gave you a container of water and said, okay, here's the lab for today. You need to make it into ice. And you know the water freezes at 0 degrees Celsius. So if you want to freeze it, what has to be the relative temperature of the container that you put it into? More or less than 0 degrees? Less, okay? You're not going to freeze water by putting it into a container that's at 1 degree Celsius, okay? You're not going to freeze the water. -1, hey, at least you have a chance. So if you're, here's the point of the story, is that if you're going to cool something down by the traditional method, you have to put it in a container that's cooler than what you're at, okay? Well, when you get to absolute 0, you can't have anything cooler than absolute 0 in terms of removing the thermal energy. So if you look at entropy as a measure of temperature, so basically what you do is you take these atoms, single atom, and you lock it in place with lasers. So the lasers act as like a jail cell. So it's like taking Cohen, and we're going to trap Cohen in a set of lasers where Cohen can't move. So if you look at temperature as a measure of entropy, which is disorder, so basically what we've done is that we've taken the single atom, we're bombarding it with lasers so that the particles can't move. So this is just one atom. So don't think like, oh, the whole room is this cold. No, this is one particular atom that we've trapped in a laser that we've cooled down to this temperature. So on this one on 34, then it says, hey, what is the deBroglie wavelength? How many times larger is this than the 0.25 nanometer of the atom? So on this one, you need to find the kinetic energy. So you can use kinetic energy equals, this is this 3/2, and then you have Boltzmann's constant times your temperature. Make sure you convert that temperature actually into Kelvin. So if you do that, you get a really small value, of 2 and some change times 10 to the negative 30th joules, okay? So then when you get that, then you can plug that into that energy equation and get the momentum. The momentum is an extremely small value. Your momentum is 10 to the negative 28th. And then once you get the momentum, then you can find the wavelength. So your wavelength, which is what this would occupy if it could, is around 860 nanometers. Okay? So you got to go through some processes. You got to find the kinetic energy, and then you got to find the momentum, and then from there you can find the wavelength. So your wavelength in nanometers is around 860. So that's the wavelength occupied by this whole thing, is around 860. The diameter is 0.25 nanometers. So that's just the nucleus itself, okay? So on a comparison of that, you're basically take that first answer and divide that by 0.25, and you're going to get about 3,500. So the deBroglie, the whole point of this is just a magnitude of comparison. So even at 0.1 Kelvin, microkelvin, the wavelength of that particular atom that it would occupy as far as like a standing wave is 3,500 times greater than the nucleus itself, okay? So the reason I picked that question is that, so everybody says, hey, we're going to split the atom. Okay, just think about this. To split the atom implies what are you going to split apart?
Nucleus.
The nucleus. So this is why splitting the atom, you say, oh, it's not like splitting the atom. That is the most over or understated, depending upon your perspective, statement that exists. Because, you know, here's this whole thing. The nucleus is a dot right in the middle, held together by the strong nuclear force that holds the protons and neutrons together. So here you are, imagine this. You have an atom the size of Chief Stadium. The nucleus is a baseball in the middle of it, on the 50-yard line. And the baseball is held together extremely tightly. And you're going to randomly shoot BBs at the baseball in the dark to try and split the baseball. Good luck. Okay? It's like, okay? And then you have to hit it just right with enough energy to split the baseball. That's the challenge of splitting the atom. Okay? That's why it's so tough to do. Okay. All of your answers on 20 should start with a 4. On 20. All of them should start with a 4. And just get progressively smaller. Are we good? Any questions? Charles?
Yeah, question 15.
Okay. So, this boils down to some fancy math. Question 15?
Yeah.
Okay, give me a second.
I didn't mean to rip it. No, Rashawn, I purposely tried and rip my paper and have to piss off.
Okay, so start with this idea, Charles. You have an electron and proton. Do they both have the same charge? Q is the same for both, right? Good with that. So you're told that they are accelerated through the same potential difference. So if you look at, say for example, FEC, right? So if they have the same potential difference, and the same charge, is the same force gonna act on them?
Yes.
Okay. So, if you could look at this in terms of work, and assuming that the distance is the same, if it's the same force acting across the same distance, are they gonna undergo the same change in the kinetic energy? Okay?
Yes.
So they're both gonna end up with the same change in the kinetic energy. Good with this?
Yeah.
We're good so far. Now, here's where you can get a little bit catchy, I guess. So, you know, lambda, the wavelength equals what? H over,
What's on?
just stay with me here.
Yeah, no, I had my equations mixed up. My equation sheet's mixed up.
Okay,
I know you didn't care.
but I do care, okay? So here's the story. So this is what you've got. So yesterday we came up with these equations that said that you can rewrite this, and there's some different ways you can do this, but this is if you substitute in like the kinetic energy part of this, you get mass times, and I gotta remember this because it's so rare, 2K over M, right?
Yeah.
Okay, cool with this. So, if they have the same kinetic energy, okay, and they do, look at what happens to the impact of the mass. Which one's going to have the bigger mass? Because your H is a constant, right?
Yeah.
So look at the impact the whole key to this is that, do you understand that they have the same kinetic energy?
Yes.
Then from there, then you're off to the races. Does that get you where you need to be? Because then look because this is Planck's constant, right?
Yeah.
Okay? The kinetic energy is the
It's
same.
the same, yeah.
So then you have that mass. So then if you were to substitute in the mass of an electron versus the mass of a proton, with the same value of K and the same Planck's constant,
Yeah.
look at the impact that would have on the wavelength. Okay?
I think that's
All right.
pretty sure that's what
Okay. Good with that? Charles, did I answer your question?
Yeah.
Okay. All right. Get that handed in. Danny, stop the camera for a second.